Let's now look at how we would solve a linear inequality if the variable is not already by itself on one side. Well, it turns out solving a linear inequality is pretty much the same as solving a equation. We're going to isolate the variable by doing all of the same types of steps: adding terms to both sides, subtracting terms from both sides, multiplying values on both sides, dividing values on both sides. We just need to make sure we do the same thing to both sides. There is one difference, and that has to do with a certain situation involving negatives. When we multiply or divide both sides of the inequality statement by a negative number, we must switch the sign of the inequality symbol. So let's take a look at why that is. If we look at a real simple inequality, 2 is less than 3, on a number line, we can see, if here's 0, 1, 2, and then here's 3, we actually have 2 to the left of 3 on the number line because it is less than 3. When we negate both sides by, say, multiplying by a -1, let's look at the relationship with those two new numbers on the number line. Well, a negative result for a number on a number line is going to be exactly opposite or across from 0 from where it originally was. So -2 would be right here, and then -3 would be here. And when you look at their locations now in relationship to each other, -3 is now further to the left and therefore is smaller or less than -2. So -2 is bigger, so we would say -2 is greater than -3. So notice the symbol between the numbers switched when we negated them. So this is going to happen anytime we multiply or divide both sides of the inequality statement by a negative number. It doesn't happen for a positive, just for a negative. It has to do with the situation where the left and right sides of the inequality are flipping across 0 on the number line, and so end up with the opposite relationship when you do that. So let's take a look at a few simple examples to just really emphasize this idea. First off, -2x is less than -8. Now, I actually meant this to be a +8, so I'm going to change that right there. So -2x is less than +8. What we're doing here to solve for x is we need to remove that -2 that's next to it. Now, -2 is multiplying x, so we're going to divide both sides by -2. And because we're dividing by a -2, the inequality symbol is going to change. So we're going to have x is greater than, well, 8 divided by a -2 is -4. So because we divided by the negative, we switch the direction of the inequality symbol. So it goes from a less than to a greater than. In the next example, -2x is less than -8. Again, we're dividing by a -2. So because we're dividing by a negative, we're going to switch the direction of the inequality symbol. So this becomes x is greater, and now a negative divided by a negative is a +4. But again, the direction of the inequality switches when we divide by the negative. Now in the third example, if you look closely, we have a 2x is less than -10. When we go to get x by itself, we're dividing by the 2, and that is positive. Because it's positive, the inequality doesn't switch, regardless of what the other number is. Sometimes people think that the -10 influences whether we change the direction of the inequality symbol, but it doesn't. The only thing that matters is what we're dividing by. And we're getting rid of the 2, so we're dividing by a +2. So x is less than -5. The symbol, the inequality symbol, stays exactly as it was originally. Same thing in the next example. X divided by 3 is less than -5. I need to remove a +3. Because it's divided, I multiply by 3. Because I'm multiplying by a positive number, the inequality symbol doesn't change. -5 times 3 is -15. In the last example here, I'm dividing by a -3, x by a -3, so I need to multiply by a -3. So x is greater than 6 because not 6, but by 6 times -3 I have to change that inequality symbol because I'm multiplying by a negative. 6 times negative 3 is negative 18. So the final result here is x is greater than negative 18. So be really careful about when you switch the inequality symbol. It's really important that you do, but only do it when you are multiplying or dividing by a negative. My screen's flashed briefly there. I don't know if you saw it on the video. I don't think it interfered with anything we were doing, so I'm just going to keep going. All right, so here are two inequalities for us to solve. Let's go ahead and isolate x in both of them, and then we're going to state our answers in two ways, in a graph and in interval notation. And then we're going to look at how we can check our solution set. 10 minus 8x is greater than 26. To solve this, we need to get x by itself. Well, we've got a 10 over here and a negative 8. Now, the negative 8, it multiplies x, but the 10 is really adding on. So we need to move that by subtracting 10 from both sides. So we have negative 8x. 26 minus 10 would give me 16. Notice the inequality symbol doesn't change when I add or subtract. Next, I'm going to divide the negative, both sides by negative 8. And because I divide by a negative, I'm going to have to switch the inequality symbols. So x ends up being less than, well, 16 divided by negative 8 is negative 2. So let's express this solution set as a graph, and then we'll express it in interval notation. As a graph, you can think of 0 as being here, and negative 2, negative 4, negative 6, 2, 4, 6. I'm just going by 2's here. And we can label, always label your number line. Oops. And if we want to be less than negative 2, I'm going to switch the color on my pen here real quick. That means I want to be to the left of negative 2. So I'm going to shade to the left of negative 2. And because I don't have an equal sign, I'm going to show a parentheses at negative 2. So I'm shading to the left of negative 2 and using a parentheses to show that I do not include negative 2. Now, in interval notation, I would go ahead and show that I want to go from negative infinity to negative 2, and I don't want to include negative 2, so I use a parenthesis. Now, to check a solution set like this, what I recommend that you do is check one point that's in the solution set and one point that's not, so that you're kind of checking the boundary. There's an infinite number of solutions here, so you can't check them all. So like I said, check one on either side. A number inside the set should give you a true statement. Something just outside the set should not. So like if we check with x equals negative 3, if I put negative 3 into the original statement, 10 minus 8 times negative 3 is greater than 26. 10 plus 24, is that greater than 26? Well, it sure is. 34 is greater than 26. That checks. We get a true statement. Then a number that's outside of the set would be like negative 1. If I check x equals negative 1, 10 minus 8 times negative 1 is greater than 26. Well, that would be 10 plus 8, which is 18. Is that greater than 26? No. So this is false, and that's what we wanted to see. That checks as well, because we want something outside of the set to give us a false statement. So what you're really doing is you're kind of checking to see, first off, do I have a true statement if I'm in the set? Do I have a false statement if I'm outside of the set? But by doing it on either side of the boundary between something being in the set and not, that gives you a clear view of whether you've got your boundary right, in addition to the two sides being true and false correctly. Let's look at the second example here. We've got 3 minus 2 times the quantity x plus 5 is less than or equal to 3x plus 8. So I have 3 minus 2x minus 10 when I distribute my negative 2. Make sure you start with your distribution to remove parentheses, is less than or equal to 3x plus 8. Next, collect like terms. Negative 2x, 3 minus 10 is negative 7, is less than or equal to 3x plus 8. Now at this point, there's two ways we can solve this. We can move the variables to the left or the variables to the right. I'm going to show it both ways. If I go with the variables going to the left side, sorry, the right side, I'm pointing to the right here, then I would have negative 7 is less than or equal to, well, I would be adding the 2x, so I'd have 3x plus 2x is 5x plus 8. Then subtract 8 from both sides. Negative 7 minus 8 is negative 15. Remember, subtracting doesn't make a difference in the inequality symbol. And then we divide by a positive 5. Because we're dividing by a positive 5, the symbol does not change. Negative 15 divided by 5 is negative 3. So I get this statement that negative 3 is less than or equal to x, or thinking about the other way around, x is bigger or equal to negative 3. The other way to do this would have been to move the 3x over. If I do that, I'm subtracting 3x from both sides. So negative 2x minus 3x is negative 5x minus 7 is less than or equal to 8. If I then add the 7 to both sides, 8 plus 7 is 15. Now I end up dividing by a negative. So notice in the other situation, I didn't ever divide by a negative, so I didn't have to switch the inequality symbol. Here, I'm going to have to do that. When I divide by a negative, I'm going to change this into a greater than or equal, and then 15 divided by negative 5 is negative 3. So here we get another way of writing it, and if you look closely, those are actually the same thing. In both cases, the inequality is opening to the x, which means that x is bigger than negative 3 or equal to negative 3. So it doesn't matter which way you move the variables to, but one direction, because you end up with a negative in front of the x, you are going to have to use the rule to switch the inequality symbol when you divide by the negative. So sometimes what people choose when they're solving inequalities is to always move the variables in such a way that they don't end up with a negative coefficient on x. But it's really your choice. But some people prefer always doing it that way without creating the negative in front of x so that they don't have to worry about the rule as often. Either way, x is bigger or equal to negative 3. If we wanted to draw that on a number line, let's say 0, I'll say 1, 2, 3, 4, 5. So that's negative 5, negative 4, negative 3, negative 2, negative 1, and on the other side 1 and 2. So now I can go ahead and shade the area where x is larger than negative 3. That would be to the right. So going to the right of negative 3. And because it can be equal to negative 3, I use a bracket at negative 3. So I shade to the right and use a bracket. In interval notation, I would simply use negative 3 on the left with a bracket going up to, comma, infinity, parenthesis. So 2 ways to express your solution set. Now, we need to go ahead and check these, and I kind of used up a lot of room, so let me go ahead and give myself some room by erasing a little bit of this. You can always back up in the video if you want to see it again. And I'll change to color green to do the check with. Now I want to check on either side. So I'm going to check negative 4 as being something that should give me a false statement, and I'm going to check negative 2. So if I check, I'll check with the one that should be a value in the set. Let's check x equals negative 2. If I put it back all the way into the original equation, 3 minus 2 times negative 2 plus 5, is that less than or equal to 3 times negative 2 plus 8? Well, let's take a look. 3 minus 2 times 3 is less than negative 6 plus 8. Keep going. 3 minus 6, is that less than or equal to 2? Well, 3 minus 6 is a negative 3. That is less than or equal to 2. So that's true, and that's what we expected. We expected it to be true, and it was. Now let's look at the other one. I need more room, so I'm going to erase a little bit more of my work here. If I can get the eraser to work. There it goes. Wasn't working at first. All right, so let's check the one that shouldn't work. So if I check negative 4 here, which shouldn't work because it's outside of the solution set, I put in 3 minus 2 times negative 4 plus 5 is less than or equal to 3 times negative 4 plus 8. 3 minus 2 times 1 is less than or equal to negative 12 plus 8. 3 minus 2 times 1 would be 3 minus 2. negative 12 plus 8 would be negative 4, and the final simplification is 1 less than or equal to negative 4. That's false. 1 is not less than negative 4, and that's what we expected. So that works as well. So again, you're checking the border, and you're checking that something is not working and something is appropriately working. So